A very good afternoon to all of you. I hope you all can hear my voice clearly and see my screen too. Let's start with today's class. Last lecture we spoke about measures and methods to control noise. We looked at source, path, and target or the observer analysis. We continue talking about noise control in today's class as well. Today we will talk about certain aspects of noise controls like use of sound barriers, use of enclosures and absorbers. So we are going to talk about these three aspects of noise control. So let's go through them one by one. Sound barriers are very important. Two people sitting in an office, on two different desks, sometimes put a small barrier in the middle that causes sound barrier. They are effective, but in most of the cases, they are overestimated in a sense that we presume that they will offer a lot of sound insulation, but we will see that in practice they don't offer that much of sound insulation. Good afternoon, Aman. Welcome to the class. So, what happens is if its sound barrier is small, then the sound through the barrier is very less important and the sound around the barrier. Sound can be diffracted easily, and the as if the open area is large around the barrier in a room, then the net transmission loss becomes independent of the transmission loss of the wall itself. We have seen this graph in the last class. You can see that if there is a barrier of a 50% of the area of the wall, rest 50% is open. Say for example, if you have a room of height say 8 feet, then you put a barrier of 4 feet height, then you can see that the transmission loss almost becomes net transmission loss almost becomes horizontal. That means it does not change at higher dB values. So here are different examples of this kind of transmission losses. So for example, this is a room here, a ceiling has been placed, the room has two desks, this is desk 1, this is desk 2. Let us say that this desk is the transmitter of the sound or the source of the sound, while this particular desk is the receiver of the sound or noise. Then the sound can travel from desk 1 to desk 2 by various ways. They have put a sound barrier in the middle, assuming that it will block some sound. Now the transmission of sound can happen through the barrier. So this is straight line path. It will get through the barrier, transmitted and come here. So the straight path. Then the sound can travel through diffraction. So if it is around the edges, then it may bend and then again it reach to the receiver. So path SBR, and it can reach to the receiver by multiple reflections. So it can go by SAR, SDER, etc. So these are the reflected paths possible. Transmission of a sound. Now diffraction, if diffraction is the only cause, suppose I exclude the other causes, let me go back to the previous one. Suppose this wall is very thick and heavy, then very little will be transmitted through the wall. And if you put some perforated coating, I will come to it later, then very little will be transmitted. And if you put an absorbing ceiling, sound absorbing ceiling, then again reflection can be reduced. Under that scenario, diffraction remains the most dominant way by which the sound will be transmitted. But remember, the diffraction involves frequencies. At certain frequencies, the diffraction will be maximum, and at certain frequencies or wavelengths, diffraction will be minimum. So basically, it can be given by something called as Fresnel number. So Fresnel number is given by n is equal to 2 by lambda a plus b minus d, where a is this straight path, b is this path, and d is this otherwise the straight path from source to receiver. So Fresnel number actually governs how much sound is being transmitted due to diffraction. Typically, the graph of the Fresnel number and attenuation is given by this. Larger the Fresnel number, look at it, larger the Fresnel number, the more is the attenuation. Practically, it has been observed that attenuation does not go beyond around 25 dB. There are reasons for it, straightforward reasons. Going back to the previous slide, if you need larger Fresnel numbers, then you need to have large A and B. Remember, it is inversely proportional to lambda. I'll come to it later. It A and B needs to be large. A and B needs to be large means source and receiver should be far from the wall, and D should be small. So it's a very peculiar. Typically A and B should be large, so you have to be a source at a large distance. R is the large distance, and the barrier height should be more. Okay, so all those requirements practically are not met. Typically these kind of arrangements are done in small rooms where A and B will be small. So in this case, there is an upper limit up to which it can work. It also depends how is the ceiling. As I told you earlier, if the ceiling is simply a plaster and paint, it will reflect lot of sound in the other room, affecting the sound propagation. If the ceiling has absorbing coating or some tiles which absorbs the material, absorbs the sound, then in that case the sound by reflection from the ceiling becomes much less. Also, what matters is size of the opening above the barrier. If you remember the diagram, office diagram, then suppose if the height of the ceiling is 9 feet, barrier is up to 6 feet, then the 3 feet is open. So that barrier, if it's small, less sound will be transmitted. If that barrier is large, then more sound will be transmitted. Also the size and the type of the wall. The wall is thick, thin, small, tall, etc. All those are going to play a role in how much sound is transmitted through the barrier indoors. What happens outdoors? Now this is one of the images that I have clicked on the Eastern Freeway while traveling to college, early morning lectures. Those were the great days. We all used to travel. I was checking some of the old photos and realized how much life has changed. Nevertheless, coming to the topic, you can see that this freeway has a wall made at the left side. This entire wall is a barrier, completely a barrier to prevent the view from the other side and the noise and the sound due to vehicle going to the other side. So this entire wall is for that purpose. So what happens is source receiver distance is great when you go to outdoors. So in an indoor rooms are small but outdoor distance is large. The Fresnel numbers are typically very large because remember those A and B are large here, and therefore you require higher barriers to control the sound. Even the ceiling is, there is no ceiling here, so the depth or height of the barrier, height of the space above the barrier is fairly large. Of course, there would be some wind loss also. So if the wind is blowing, sound will be carried from one side to other side, which we typically don't assume indoors. And reflection here is not a cause if you are talking about outdoors. So these kind of sound barriers are often put, they offer some protection from the sound, not a large protection. They are commonly overestimated. They are more effective at higher frequencies or at smaller wavelengths. Remember, Fresnel number was inversely proportional to lambda. So smaller the smaller the wavelength, larger is the Fresnel number, and therefore more is the attenuation. So higher frequency gives a smaller wavelength. So these kind of barriers are more important at smaller wavelengths or higher frequencies. Then comes the next idea for controlling source noise is or are enclosures. Typically in an enclosure what we do is if there is a noisy source of sound, we put it in an enclosure. I'm going to demonstrate a very simple experiment, but the similar logic will be applicable to other extensive cases. So I have a buzzer here, a typical bell. This kind of bell might be at your home, etc. It gives me a continuous sound of 83 dB if you put it on. Now if you put a simple acoustic tile container absorber kind of it, you still get around 81 dB. So you can see that it is not very useful in a sense that a lot of sound is leaking out. Only 3 dB drop has happened. If you keep it on an absorbing panel, then remember here it acting like a point source. Here half the sound will be absorbed and it will be down by 3 dB. The resulting sound decreases to 30 dB. Then if you cover it by a metal can, cookies can, etc., then it has been observed that it drops to 77 dB. So there is a considerable drop of 6 dB from 83 to 77. Now, if I use both a padding at the bottom and the can at the top, then the overall drop is around 72 dB. And finally, can with absorbing material. So you can see that the inner lining of the can has put an absorbing. Here the absorbing material was exposed. So a lot of transmission happened and sound comes out. But here what will happen is the can will block a lot of sound. Absorbing material is inside, and if you cover, then it's a 69 dB. You can see that there is a huge 14 dB drop from 83 dB to 69 dB, and that's a much drop in the sound noise transmission due to an enclosure. So these enclosures are very important. And for example, if you have a heavy machine operating somewhere, it can be put into an enclosure. In fact, an auditorium, a theater, an auditorium actually is a noise producing machine. You can imagine. Like imagine an auditorium, say 100 people sitting inside. People don't make noise, but movies are playing or some theater drama is happening, and there is so much of noise, so much of loudspeaker noise is there. So it's a source of noise. Outside people must not expose to this source of noise. So these kind of systems are used. You will find that inside an auditorium, entire surface is carpeted, ceiling, walls, flooring. Of course, apart from controlling the reverberation time, they also absorb excess sound and doesn't allow that sound to go out. These are some illustrations where you can design these kind of systems. So this is the source of noise. It could be an orchestra playing on the theater or maybe a machine, etc. You can see that we are using the same principle. We have spring mounts, we have enclosures which are padded from inside. These enclosures are padded from inside all the time. Some places you may require air conditioning or you may require ventilation. So you can make a double wall perforation. You can see this is inner wall, this is perforated, this has absorbing material here, this has absorbing material here. Outer wall has an absorbing material. You might put another um, outer wall so that there is no contact between outside world and inside, no structural contact, so that the sound does not travel through the solid walls. The air can enter from one end and it can go on the other side. So this is an example of these kind of design. This is another kind of design which is used to shield a small motor. There is a fan over here that will put the, or a fan is here that will pull the cold air inside. Air will finally go out. Inner linings, inner surfaces are carpeted so that the most of the sound is absorbed. Sound absorber, as you can see, play a very important role. Sound absorbers are nothing but some material which is soft, highly perforated. For example, a thick, soft curtain, a towel, a carpet, a cushion, all these can act like sound absorbers. Typically, the sound waves are trapped inside the openings and cushions, and that energy is converted to heat energy. Porous materials are important for this. If the material is hard and polished, then this kind of transmission does not happen. The As we have seen in earlier chapters, the sound energy is a very small part of the overall energy in the system, and therefore the rise in temperature is very less, almost negligible. Therefore, they can be safely put at various places. Porous materials are more effective at higher frequencies than at lower frequencies. The porous materials are now available in the form of acoustic tiles, and there are typically of two types. One is one in which the ordered holes are placed. They are the holes are the placing of the hole or spacing between the holes can define the absorption maxima or a particular frequency. So they are very useful in cases where the sound generation happens at a particular frequency. Then they can absorb those frequencies. And random holes will have broader absorption frequency pattern. So there are two examples. Here is one. There is a solid wall, and there is a this is a width of the panel. It is stuck to the wall. This is mostly the porous material, and it absorbs lot of sound. The other example is similar one. You have the porous material, but the front panel has holes at some intervals, some regular intervals. These holes are going to trap the sound, and the pores inside or small openings inside, they are going to act like Helmholtz resonator. They resonate, absorb lot of sound energy, convert them into heat energy, and that is how the sound energy level is reduced in this. These tiles are available commercially. You can just Google them and you can find a variety of it. I'm sure many of you have seen these kind of tiles. They are placed in our college in MMR, Multimedia Room, if you have ever been, or SCAVI, if you have ever been, then you have seen the walls are perforated with tiles. That's how they look like. People sometimes make false ceiling with perforated tiles, etc. These are zigzag, perforated plus zigzag. Zigzag tiles increase the surface area and therefore increase the absorption of sound manifold. So sometimes even these are preferred. In this lecture, we can stop at this point. Thank you. I will share a Google Meet link to have a common discussion.